Good morning, good lunchtime. Welcome to our Ask the Expert. Today we're joined with George Maddison, who's our engineering lead for additive manufacturing, and Carol Mazzina, if I pronounced that correctly, who's one of our doctoral researchers and uses facilities here at the RDC. I will hand over now. George will be taking some questions. Do pop your questions in the Q&A tab. We have got a couple that have already been submitted, but just to let you know that the chat facility, we won't be moderating that. We're not looking at that. So do put your questions in the Q&A instead. I will hand over to you guys now.
Great. Thanks, Ray.
Thank you.
Okay. I can't see any in the Q&A, so Carol, if you want to kick us off.
Okay, let's start with hopefully a simple one. Why would somebody choose to 3D print a part as opposed to casting or machining it? What are the benefits of AM?
Yeah, so there's quite a broad range of things that you would consider. It's never going to replace, for sheer efficiency, something like manufacturing of cutlery, for instance, where you're stamping out and forging and very quickly finishing parts on a vast scale. But for example, rapid prototyping of new designs, that's one very effective way of generating parts. So, for example, if you want to make something like a forging blank, for instance, that you design your tooling from, or the tooling itself, you can 3D print it to create the unique geometry without having to design a whole set of tooling and then test to see if it works, tweak it, and then have to redesign it again and tweak it. You can very, very rapidly hone in on that specific shape. And from that, you can then take your shape complexity, as far as you want to take it, within reason. It can't literally do anything. But you can make stuff that's, not manufacturable in terms of its complexity by any other means. The second option, and very much on the metallurgy side of things, is the specific metallurgy of the alloys that you want to manufacture using this method. So similar to casting, forging, rolling, it's a tool in the arsenal of the metallurgist, certainly for here in Sheffield. When you manufacture things through additive manufacturing, particularly with laser powder bed fusion or DED, you end up with a very specific microstructure. And because you're using something like a laser or an electron beam, very often you get very rapid solidification, particularly with the laser-based side of additive manufacturing. That generates very fine grains in your material. And in metallurgy, there's something called the Hall Petch effect, where the smaller your grains get, the stronger your material becomes. And because you've got such small grains in your material, you end up with very strong material that's been 3D printed. And different processes will give different resultant microstructures. Something like binder extrusion, where you have a binding material. That's all solid state. There's no melting involved, so the grains will naturally grow during the sintering phase of that process. And you end up with a much more equiaxed microstructure, whereas with laser powder bed fusion with DED, you end up with quite columnar structures. So the tailorability of the processes that are available differs with different types of additive manufacturing, but there's a lot of flexibility. And if you choose the right procedure, you can get basically tailored microstructure for what you're aiming for.
You've mentioned LPBF and DED, so just for the people that are not very familiar with the AM side of things, what do these acronyms mean, and what are the different types of processes that are available?
Yeah, so additive manufacturing is not a single process. It's a family of processes, and it's not just for metals, it's for polymers, it's for ceramics, it's even for regoliths. You can even print, there are printers on the market that print wood these days. The main ones that I've referred to laser powder bed fusion, directed energy deposition. These are two systems or two processes that we use quite a lot here in Sheffield. So laser powder bed fusion is, as the name suggests, a laser-based process where we have a bed of powder and we are fusing it together. So that's kind of like where the acronym comes from. What we do is we take a metal plate that we start off with, and we spread a very thin layer of powder across, and we use a laser to melt a shape into that powder. That fuses with the plate beneath it. The whole plate drops, you scrape a new layer of powder across, and then repeat that. And the laser can change its shape, the shape that you're producing. It can be something simple like a cube, or it can be something extremely complex like, say, a turbine blade with interior structures. Every layer it can change, or it can even be continuous cross-section. That's also possible. But then you'd argue you might as well extrude the part. So that's laser powder bed fusion. Directed energy deposition. There's two different types of this. You can either use powder or you can use wire. And you can also use different types of energy sources. So again, similar to laser powder bed fusion, it doesn't actually have to be a laser. You can also use electron beams, and with directed energy deposition, you can use electron beams, or you can even use something like an electric arc, to melt your material. That generally tends to be for wire-fed processes that are directed energy deposition. But the process fundamentally is you have a feedstock and you have an energy source, and the feedstock passes in front of the energy source, and this energy source moves around with the feedstock, and you deposit a structure like a giant weld bead, effectively. And if it's wire-fed, it's usually called wire arc additive manufacturing. And if it's powder-based, it's usually with a laser, and it's called blown powder directed energy deposition.
Let's answer the first question in the Q&A. Kareen's asking, what are the little cubes that people make you make all the time?
Yeah, so here at Sheffield, we specialise quite a lot in novel material development. So the machines that we have are specifically designed for ease of cleaning, very robust cleaning, so that we can change materials without having to worry about contamination. And what it means is that we can develop things like processing parameters and learn about the specific metallurgy of either very well understood alloys or totally novel things that have been designed by academics that are in a conceptual state. And we can take that from conception to reality. The first stage in any new development of any material, most of the time, is to print a small test piece and to see what has actually been produced by the process. Now, there are various parameters that we can influence, and most of the time that generally tends to be the processing laser or energy source that we're using. So if it's electron beam, it's the energy, the power of the electron beam, how quickly it scans, what scan pattern it uses. If it's the laser, it's very similar. We can also change things like the spacing between individual scans as we scan across a part to make a solid object. But it's also things like the ambient temperature and the base plate temperature of the processors. So the machines we have, the electron beam systems naturally, because of the process, run at a very high temperature. The laser-based systems generally tend to run at room temperature, but slowly accumulate heat over time. There is also options for preheating the stage. And all of these parameters come together, and fundamentally you form a bulk solid object. And we take it, we cut it in half, and we see what we produce. And you can either do very rough, very quick analysis just to see if there's still holes or if there's no holes in the parts, or we can do more in-depth analysis using etching, scanning electron microscopy that we have in Sheffield here as well. And we can take very quickly a material that we don't know anything about to being pretty well understood in maybe even as little as a day, just because of the flexibility of the machines. And even materials like I mentioned in my Meet the Expert video, we've printed sand, we've printed moon dust, so non-metals. Even those, we can very rapidly prototype them and understand what's happening. Obviously, we can't necessarily look at them under SEM, they're not conductive, but yeah, we can still get a good idea of what's actually happening on a small scale.
So next question follows up. What has been the most challenging material that you've printed?
So yeah, on the subject of regolith, the moon dust that we printed with Catherine Yantafi at UCL, it was a European Space Agency project. Yeah, that was very difficult. Most metals, certainly on our printers, we can manufacture to something that roughly holds its shape, even if it isn't particularly well fused together. If it's a very high temperature material, usually we can at least create something that holds its shape and holds together. With the regolith, normally we have a set of parameters such as power and speed, and with most metals, there's a kind of general area that you know to aim for. And with regolith material, because of such a high melting temperature and totally different behavior in a liquid state to metals, you had to take that initial window and just throw it, well, out the window, look in a completely different direction. And we were several orders of magnitude outside of the traditional processing window in numerous parameters. And it was only after we really sort of sat down and went through things like the thermal history of the material, how the material was behaving at high temperatures, and really gone into the literature that was available on this material, that we realized that if we could slow down the cooling process, which is difficult to do in laser powder bed fusion, if we could slow down that cooling process as much as possible, we might be able to slow down the solidification and retain heat into the material. And eventually that's what we did. And we managed to produce not fully dense, not by any stretch of the imagination, but somewhat dense material that we could then turn into compression test coupons and do further analysis from there.
So we've just talked about all of the more experimental side of things. So what are some real life applications that people could utilize additive manufacturing for?
So yeah, I mean, I guess the best way to sort of tackle that is from the top down. Is to look at what companies are already using additive manufacturing for their processes. Now, as I say, additive is not just laser powered bed fusion, it's not just DED, it's not just metals. There are a whole host of things that you can use additive manufacturing for. If you start from the very industrially heavy focused, it is very much metals. You are looking at companies like Rolls-Royce, like GE, Boeing, BAE, all interested in additive manufacturing. Siemens already manufacturing turbine blades. GE already manufacturing titanium parts for aircraft, for aerospace, for lots of different applications in there, things like Arcam machines. You then take that a step down and say, well, what are the machine manufacturers making machines to be able to do? One of the first things that Renishaw, which is a big machine manufacturer here in the UK, one of the first things they did was making Renishaw machines that were designed to make dental implants. And the great thing about additive manufacturing, and particularly the processes that we use, is you get a very high level of tolerancing very, very easily. So it's near net shape, so you have to do only minor post-processing. And it means that, for example, for bioimplants, you can make a bioimplant that is 99% exactly the same, or, you know, almost perfect fit, if not a perfect fit for the person that it's going to be going into. You can design it so that, in theory, the cells actually grow and fuse into the structure of the implant so that you get better things like osseointegration. You can create bone scaffolding that actually, in some cases, not just metals, but in polymers, you can make biodegradable polymers that actually diffuse into the body after a certain amount of time. that fit to exactly the shape that you need them to be, so that 2 years down the line after you've had, say, a very bad fracture and you put this bone scaffolding in, the polymer's totally gone from the body. It's been absorbed by the body and it's been removed by the body in a natural process. There's no lingering things like microplastics hanging around inside the body. These are all perfectly safe polymers that exist in nature. And then you come down to the sort of what I would refer to as the sort of more well-known aspect of 3D printing, which is making widgets, making jigs, making simple things that are actually quite useful. And there was a school that I went to recently here in Sheffield, King Egbert's School, and Mrs. Vardy, their design teacher, was showing her students how to design things, not just through traditional processing. When I was at school, it was very much, you use something like a lathe, or you use sort of traditional manufacturing fabrication processes. And she was trying to bring this new technology into the schools. And she was showing them how to make, or helping them design, a potato peeler. And when you think about it, a potato peeler is quite a simple object, but if you're making that, it's actually not that simple, because you've got a kind of prong shape that you then have to put a metal blade inside of. It's not necessarily a trivial shape to manufacture with, something like a piece of wood that you then whittle away, like you would have done 30, 40 years ago. So yeah, making simple things for even just for use around the house, and for use in the lab. We make all sorts of fixtures and jigs. One of the PhD students here has made an extension for one of our machines out of plastic on a 3D printer. He's made like an extender box for the back of the machine that we fit sensors into the machine with. So yeah, and yeah, everything down to wood. As I say, the manufacturer that makes the machine that prints wood, on their website, they've got things like guitar cases that have internal honeycomb structures, and it totally changes the sound that's produced by the guitar. So yeah, if you can think of an application, there's probably something that you can fill a niche with.
So what would you say is the coolest thing that you have printed so far?
I mean, the moon dust was good. I think I'm allowed to talk about it. I think the coolest thing that I've printed was for a Royce project, which is technically still ongoing. And it was some titanium frames that were originally, I believe, 1/4 of a millimeter thick in terms of their struts. So these very, very thin A-frame sort of shaped struts. But not only were they very, very thin, they were also hollow all the way along. So it was truly a structure that couldn't be manufactured in any other way other than by using additive manufacturing. And I think that's probably one of the most complex things that we've done. Just anything with sort of really high complexity that's not manufacturable by any other method. Even things like lattices that if you Google additive lattices, you can find hundreds of pictures online. They always look really nice, and they're always interesting when you're making them, but finding a use for them when they actually have a purpose rather than just to look pretty. So one of our academics here is making magnetically graded lattices, where some of the nodes are magnetic, some of the struts are non-magnetic, and using additive manufacturing to control where the magnetism is in that lattice. I think that's pretty cool. And there's loads of applications for that in motors and in terms of crash barriers and plating and that sort of thing. Yeah, really good applications.
What are some other collaborations that you have done here at the university, just to give people an idea of what these processes can be used for?
Yeah, so one of the more recent ones that we've done is with a company here in Sheffield called Ernest Wrights. For people listening, that name may ring a bell. If you go into your kitchen and look in your top drawer, you may find a pair of shears or scissors that have Ernest Wrights stamped onto them. So they're a manufacturer who, from here, they are on the next street over and a few doors down. So really very close by. They make and finish shears, scissors, those sorts of things. Lots and lots of different products available. And they were wanting to prototype a set of shears that had been originally produced in the 1940s, I think it was, in the 1950s, quite a while ago. And they came to us and said, would you be able to rapidly prototype in stainless steel the part that we'd like to produce? And we said, of course, yeah, we can give it a go. And rather than what their traditional, as I mentioned previously, their traditional manufacture route, or sort of route to being able to produce these parts, would be to produce tooling, get small rods, and then stamp forge them out into the correct shape. But to make that tooling in the first place is very, very costly. It's very iterative. If there's slight problems with the initial design, you then have to go back and completely remake the tooling again, which is usually in some kind of big cast iron block. It's very expensive, very material heavy, and if you get it wrong, it's quite a lot of time and effort. And so what we do is we sort of cut out that middle step by simply printing the original forging blank for the tooling. I've actually got it here. Here's one I made earlier in the best Blue Peter fashion. So I'll hold it up to the camera, but this is a piece of stainless steel. And this is the initial design that we made, and this is for a set of rose shears. So this is like your garden shears. And you simply, great thing about this design is you simply take a second one of these and attach it here, put a pin through the hole, and you've got a pair of shears that you can use to cut paper or cut roses if you want to. So yeah, and again with the sand printing, so that was in-house here with Professor Colin Smith. The idea of that is you take, say, a 3D printer, laser powder bed fusion, into an area that has lots of desert sand. Desert sand is not very good for construction. The thing that makes sand useful for construction is it's not a spherical particle. It's very angular. Most sand that's used in construction is ground manually through industrial processes and turned into sand from larger pieces of rock. And so you get this, it's effectively percussion atomized in powder sense. Whereas desert sand is gas atomized in the powder manufacturing sense because it's been eroded by the wind over thousands of years. And so when you put it into sand, there's no angularity, there's no natural locking that occurs between the sand particles and the cement. And so the strength of that kind of cement is very, very poor versus something that uses very angular sand. So it's a big part of what provides the strength in the concrete or in the cement. And so to find a use for desert sand, because there's quite a lot of it out there in the world, we thought, well, you could either try and melt it into a rough shape or sort of semi-vitrify it, semi-solidify it, sort of sinter it together. You could sinter it, but that is quite an energy-intensive process. You've got to heat a furnace up for however many hours just to make a few bricks, and you'd have to find some way of dividing them so that they don't all stick together. The alternative is to use a solar collector, and it's not solar power where you have like a silicon panel. It's literally a series of mirrors and lenses that takes the sunlight and focuses it into a beam, which is then used to melt the sand. And in theory, you can produce a similar kind of energy to what you get on our lab-based systems. You probably want to scale it up and make several to speed up the process. But the idea is you take one of these printers out into the desert, you scoop up sand in a big spade and just pour it in. And then a few hours later, a brick pops out. And it's a very efficient way of making construction materials in areas that have lots of desert sand. And so when we did this with Professor Smith in civil and structural, we made coupons like this. So this is a compression test coupon, and that was taken. There was 20 of them in total. They were taken, and they came back as strong as bricks when they were compression tested. So it was achieving the end application. So that was also quite a cool application.
Have you since then printed a full-size brick?
Yes, we did. We did print a few large pieces, larger test specimens. Again, our machine is probably 140 mil diameter, so it's still relatively small. So I wouldn't say it's necessarily a representative brick, as it were. But in terms of what looked like a small Lego block or like a Duplo block, was the idea. But yeah, we did print some larger test pieces as well, and they also came out quite strong as well.
So I know that you've done some collaborations with other universities as well, and like nationally even. Do any of those stand out, or were any of them worth mentioning?
Yeah, I mean, there's a couple of ones recently. I've been working with a couple of chaps from Cambridge, and they're looking at specific microstructural control in different types of steel. This is really good. It's already led to a publication that's recently just been submitted. So yeah, it's Matteo Saiter and Dylan Skelly in Cambridge. Their work really fascinating. Would recommend people to go and look at it. It's basically looking at microstructural control in steel, and as I was saying earlier about things like the magnetic steel that we work with here, it's the same material. By using the printers to control the microstructure as we print the parts, so that some bits are magnetic, some bits are non-magnetic. You don't have to change materials; they all fuse together, but some regions are magnetically graded. And you end up with a part that's actually functional or just from one piece of material and has some kind of magnetic functionality, or is designed to collapse in a certain way or at a certain rate when you compress it, that sort of thing. So it's kind of the next step for additive, certainly in the metals side of things, or one of the next steps is being able to actually control specifically what's being made, rather than just saying, have we made a part that hasn't got holes in it? Because we know we can do that. We know we can do that for quite some time now.
So if someone is out there listening right now who's considering using additive manufacturing for some project, what are some special considerations that come with additive manufacturing that they should keep in mind while trying to decide?
So I think the most important thing to say is it's not a silver bullet. It can't do literally everything. It can't do certain features, so things like overhangs. If they're too large, the part won't build properly. The parts are they've often got kind of sort of poor, not poor, but not as good surface finishes as to something that maybe was cast or forged directly out of the machine. You can then do some post-processing on the part afterwards, but of course it's another step. The important thing about additive is to consider it as a processing step, not just the whole process in and of itself. It's part of the metallurgist's or manufacturer's arsenal. So that would be the first thing I would say. The second thing is that if you're going to make a part with additive manufacturing, look up design for additive manufacturing and design your part from the beginning to be for an additive process, because very often what we've had as this technology sort of come into the industrial space is that a lot of people have said, well, can we print an existing part that we already have using this process and make it more cost effective? That's all right from a sort of cost effectiveness side of things. But if you're making a part that's just, a banana shape with a few holes in it, you could easily do that much quicker by stamp forging it out and then machining it afterwards. And it's going to be much faster. You're going to generate more parts, and you can automate it as well in this day and age using robotic assembly. The thing about additive is that you want to take advantage of the true free form capabilities of the machines. If you look at something like topology optimization, they're producing parts that are much more natural in their structure and design than what humans have been able to conceptualize or even make for the past tens of thousands of years. If you look at something like a lily pad or a tree or something like that and how the structure branches out, it's only with additive manufacturing that you can actually generate this efficiently. Otherwise, you're there for ages taking tiny bits off of a solid piece of material. But if you're going to create a part with additive manufacturing, do it from something that's been designed for additive manufacturing. Really take advantage of the freeform capability. There's a company called Leap 71 that they produce things like rocket engines, but what they're also looking at is AI designed components as well. And some of these things are absolutely crazy. Like the humans would never be able to not conceptualize it, but it would take a very long time for humans to specifically create something in CAD, even with automated tools that's as complex as what the AI is capable of driving and producing. And I think that's the next step, is you almost have to sort of forget a lot of the sort of traditional design techniques and think of it as a process that produces an end result.
So earlier you've mentioned or touched on the kind of high tolerances that you can get with the process. And considering that a lot of companies are from the aerospace and automotive sector, where you do need like really tight tolerances and high accuracy, what kind of level of accuracy and reliability of these parts can you get from the process currently?
So, I mean, the big one is, can we print it fully dense? So it doesn't have defects, doesn't have holes. And the answer is that with proper material development and proper testing, I mean, in aerospace, for example, it's 7 years from part conceptualization to actually being used in an aircraft. With proper testing, and as long as you're quantifying the processing from start to finish, you can get stuff that's equal or sometimes even better in quality than stuff that's traditionally manufactured. Again, it comes down to your design from the beginning and designing in for the part to be made with additive manufacturing rather than trying to make a traditional part with additive manufacturing. It's in terms of tolerancing, naturally there's a limit to what we can achieve with something like powder bed fusion. The size of the powder particles, that's quite a major factor. The energy source spot size. So, for example, with laser powder bed fusion, you're limited to around 60 to 80 microns with our machines. So anything smaller than that. And it's not guaranteed to actually reach that level of tolerance. Excuse me. In terms of tolerancing, if you're making a multi-stage assembly, it depends on, again, how complex it is, but you can usually get things that when you printed them, especially if they've come from the same machine, you can have things that can either be assembled very rapidly after they've been taken off the machine. You can even make things, you've probably seen it online. There are articulated lizards that all, when you take them off the blade, they sort of all all the links are already interlocked or locked together. You don't have to ring them together like chainmail suits. Excuse me. Chainmail suits. There are videos, again, you find them on YouTube, of someone taking a chainmail suit out of the printer, breaking it in certain locations, and then unfurling it into a full vest. And, you know, like the tolerancing on that it doesn't look particularly impressive at first, but when you realize that the part has been constructed and then been designed specifically to break in certain locations so that it all unfurls out, and it's all still interlinked together, it's actually quite good. And the thing that particularly powder bed fusion and DED struggle with are things like overhangs, and sort of overhanging features and rough surfaces that arise from that. If you come at it from the perspective of designing something for additive manufacturing, you can either counteract for that, make sort of maybe like a teardrop shape hole that will then deform into the correct size, or you can just not bother. If it's a very small hole, don't even bother printing it or print a small pilot hole and then just tap it out and drill it afterwards. Especially with threads, Additive struggles with screw threads, but it's often better to tap those afterwards.
So to finish up, I'm going to ask you one last question. What is the most annoying thing about your job?
Yeah. I think, probably having to choose between whether we do something or not, or having to prioritize like certain specific jobs over others. So most, if not all, of what we get that comes to us as like, can we manufacture this or can we do this? It's all really cool stuff. Like everything that we get asked to do is fantastic. You know, it's really cool. It's really interesting. And particularly with things like the Royce Access Scheme, there are conditions on whether or not we can do it, such as, you know, is the equipment available at the home institution of the person who's using it? And if it is, we have to say no. And it's really unfortunate sometimes because there's some really cool projects that, you know, we otherwise miss out on. It's not happened too often, but it does happen every now and again. And then I think probably the only other thing that kind of annoys me is that naturally the machines can be temperamental. It's new technology. There are some issues that arise from using the machines on a very, very heavy basis. Not as heavy as it would be used in industry, but then it's not designed to be used industrially. So yeah, just being able to get all the work out in a timely fashion, I think, something that we're working on, but it does frustrate from time to time.
Pop my audio back on now. Thank you so much for joining us, George. It's been really interesting to hear about what you get up to down in the workshop.
Pleasure.
And thank you, Carol, for hosting us really and asking those questions. For anyone else who would like to know more about Additive, please do feel free to get in touch with us. You can email royce@sheffield.ac.uk, and you can find out more on our website, which is www.sheffield.ac.uk/Royce-Institute, and we would love to help you with your next project. Thank you very much for joining us.